Hey there. Today we're diving into reverse engineering with FreeCAD. Our mission is to recreate this mountain bike disc rotor, and we're going for perfect accuracy. You'll see we can get it bang on, even the weight will be the same. And you'll also see that FreeCAD is actually really good for modeling parts like this accurately and without too much hassle. I'm going to walk you through my go-to methods for getting all the measurements and then rebuilding this thing in 3D. I'm hoping this can be useful for your own projects down the line. As always, you can download all the files to follow along with the tutorial from my Ko-fi page. That includes the sketch images and the 3D model. It's completely free, but if you'd like to support the channel and help it grow, you can leave a small donation. Thanks in advance. Since we're doing some reverse engineering, we need to start with something reliable and accurate. In this case, we're working from an image, because the part we're modeling is completely flat. Now, my good old trick for this kind of situation is to scan the rotor using a regular document scanner. Honestly, it's the perfect tool. You get a distortion-free image, and it's at true scale. If you don't have access to a scanner, or if your part is too big to fit, you can use a camera with the longest focal length you have. But if it does fit in the scanner, I really recommend going that route. To import an image into FreeCAD, all you have to do is drag and drop it directly into the viewport. It'll automatically snap to the top XY plane. In my case, the image is already at real scale. If that's not the case for you, you can double-click on it in the tree view and use the calibrate option to resize it properly. As for me, I'm just going to adjust its transparency in the properties view on the left and set it to 75. Another important point to consider is the different dimensions that need to be taken into account during the modeling process. To make sure the disc fits properly onto the hub, you can either take precise measurements using a caliper or look up the standard dimensions. As shown in this diagram, we need to follow the ISO 6-bolt standard when recreating the disc. The first step we're going to take is to trace the outline of the rotor and extrude the main shape. First, we need to create a body. That'll be the solid that represents our rotor. Once that's done, we can create a sketch to draw the contours in 2D. Click on the sketch icon and select the XY plane to begin your drawing. The view should automatically align perpendicular to the XY plane, just like if you were drawing flat on a sheet of paper. We'll start by tracing the inner contour of the rotor. Since we have a precise image, we can trace over the contours. Instead of using the basic circle tool, we'll use the circle by 3 points tool, which will help us position the circle exactly where it is on the image. All you need to do is click 3 times on the inner edges of the image, and the circle will be correctly placed. To stop using the tool, right-click or press Escape. To make sure the circle is the correct size, we need to give it a dimension. Typically, the inner circle has a diameter around 33.3. Using the Dimension tool, set the diameter of this circle to 33.3. As you can see, our image is pretty well calibrated because the diameter before adjustment was 33.4. If you feel like the trace isn't close enough to the image, you can move the circle to align it better. I'm being a bit picky here since the trace is already really close, but you can be as precise as you want. Once you've chosen the position of the circle, you need to constrain it to fix it in place. Using the Dimension tool, create a vertical dimension relative to the red axis and a horizontal dimension relative to the green axis. Don't enter any specific values, just leave the ones that show up, otherwise it will move the circle. Next, using the Centered Circle tool, create a circle from the center of the first circle and set its dimension to 180, which corresponds to the outer diameter of the rotor. If you've done your first circle correctly, the second, larger one should perfectly match the edges of the image. You can double check to make sure everything lines up. Here, everything is spot on. The sketch is fully constrained, and we can exit by clicking the Close button. Now, we're going to use this sketch to create a solid. To do that, click on the pad icon. You'll find it either in the task menu on the right or in the toolbar. Then, in the menu on the right, you can set the extrusion height. For a rotor, the thickness is usually between 1.8 and 1.85, so pick one of those values. Then click OK or press Enter to confirm. Now we're going to trace the position of one of the holes used to mount the rotor onto the hub. To do that, we'll create another sketch and once again select the XY plane as our sketch plane. For this sketch, we'll need the center of the rotor as a reference. To access it, we'll use the external geometry projection tool. With that tool, click on the inner circle of the rotor. This will project both the circle and its center point into the sketch. To see the base image again, click on the View section icon. Once that's done, you should see a dotted violet outline of the projected inner circle. Now let's retrace one of the small bolt holes. Using the 3-point circle tool, trace one of the small circles by clicking 3 times along the edges in the image. These are M5 bolt holes, so using the dimension tool, set the diameter to 5.5. Still with the dimension tool, set a distance of 22 from the center of the inner circle to the center of the hole. This value is very important because it follows the ISO 6-bolt standard, which will allow us to mount the disc on the hub. It must absolutely be respected. And finally, create a vertical dimension from the red axis. Just leave the default value. At this point, your sketch should be fully constrained, and you can close it. To create the hole, click on the Pocket tool. We want the hole to go all the way through both sides of the rotor, so in the panel on the right, check the box that says Symmetric to Plane. Then, in the drop-down menu, select Through All. You can then click OK to confirm the operation. Now we're going to create the 5 remaining holes. To do that, we'll use a polar array operation. But before that, we need to create a rotation axis to make sure the array works correctly. Select the inner face of the rotor, then click on the Create a Datum Line tool, which you'll find in the Datums menu. You should see a yellow vertical line appear at the center of the rotor. In the panel on the right, just click OK to confirm. Next, in the tree view, select the pocket we just made, then click on the Polar Pattern tool. On the right panel, under the Axis section, click Select Reference, and then click on the yellow line in the viewport. Now, under Occurrences, set the value to 6. Then click OK to confirm the operation. You should now have a rotor with 6 holes, ready to be mounted on the hub. Before we move to the next step, I'd like to take a moment to thank PCBWay for sponsoring this video. They're a trusted name for both DIY and industrial projects. I had the chance to test their 3D printing and CNC services to create a bike chainring, and the quality was truly professional. You simply upload your 3D file, select your options, and you're set. Their standard 3D printing options are excellent. Plus, every new customer receives a $5 coupon for their first order. A big thank you to PCBWay for supporting this video. We're going to add this decorative element in the center of the rotor. Just like we did for the bolt holes, we'll start by creating a new sketch on the XY plane. Using the external geometry tool, we'll import 2 of the bolt circles and the inner circle of the disc. These will be our reference points for the sketch. To bring back the background image, click the View section icon in the top menu. Then with the line tool, we'll draw 2 lines going from the center of the inner circle out to the centers of the bolt holes. Next, we'll draw the radius of the inner circle between the 2 lines. With the dimension tool, we can measure the angle between the 2 lines. It should be 60 degrees. Right-click to cancel that dimension and instead set an angle of 30 degrees between the radius and one of the lines. That's going to give us the center point for our decorative hole. Now select all 3 lines and turn them into construction geometry using the toggle tool. Then use the center circle tool to draw a circle at the end of the radius line. With the dimension tool, give it a diameter of 11. You can now close the sketch. With Sketch 2 selected, click on the Pocket tool. In the right-hand panel, check Symmetric to Plane and change the type to Through All, then hit OK to confirm. Now we're going to create a polar array to replicate the decorative cutout. In the tree view, select Pocket 1, then click on the Polar Pattern tool. In the panel on the right, under Axis, switch to Select Reference and click on the yellow line in the viewport. Then set the number of occurrences to 6 and click OK to confirm. Now we're going to make the large openings that help with heat dissipation and also add a bit of style to the disc. Start by creating a new sketch and select the XY plane as your sketching plane. To see the image again, click on the View section icon. Using the 3-point arc tool, draw 3 arcs following the image, 2 small ones and 1 larger one. Try to match the contours as closely as possible. Then, to keep them from shifting around, use the Dimension tool to add 1 vertical dimension from the red axis and 1 horizontal dimension from the green axis. Don't type in any values, just accept the ones FreeCAD suggests. Do this for all 3 arcs. Next, give a radius of 4 to 1 of the small arcs, then select both small arcs and apply an equality constraint between them. Now for the large arc, use the Dimension tool and give it a radius of 15.5. Then using the 3-point arc tool again, connect the arcs you've just created to finish the shape, still following the contours of the image. Set the following radii: 90 for the top arc, 75 for the arc on the right, 66 for the one at the bottom. Finally, add tangency constraints between all the arcs. Just select 2 arcs at a time and apply the tangency constraint. Once your sketch turns green, you're good to go. Click Close to finish the sketch. To create the opening, make sure Sketch 3 is selected, then click on the Pocket tool. In the panel on the right, change the type to Through All and check the box that says Symmetric to Plane. Then click OK to confirm. Now we're going to create the polar array, which will really enhance the overall design. In the tree view, select Pocket 2, then click on the Polar Pattern tool. On the right, under the Axis section, choose Select Reference. Then, in the viewport, click on the yellow line. Set the number of occurrences to 8 and click OK to confirm. Now we're going to trace the 3 small holes that help with the cooling of the disk. Let's start by creating a new sketch and place it on the XY plane. To see the background image, click on the View section icon. Then, using the 3-point circle tool, we'll trace the 3 small holes. With the Dimension tool, set the diameter of the small hole to 4. Select the 2 smaller circles and apply an equality constraint between them. Now, for the larger hole, use the Dimension tool and give it a diameter of 6. To finish constraining the sketch, you'll need to lock the center point of each circle. For each one, add a vertical dimension relative to the red axis and a horizontal dimension relative to the green axis. Once the sketch is fully constrained, click Close to exit the sketch. With Sketch 4 selected, click on the Pocket tool. In the right-hand panel, set the type to Through All and check the box Symmetric to Plane. Then just click OK to confirm the operation. Now we're going to repeat these holes on the outer part of the disk. These holes will help improve the cooling of the disk. Select Pocket 3, then click on the Polar Array tool. In the panel on the right, under the Axis section, switch to Select a Reference, then click on the yellow line in the viewport. Set the number of occurrences to 16, then click OK to confirm the operation. Now we're going to create the small cutout on the edge of the disk. To do that, we'll start by creating a new sketch on the XY plane. Using the External Geometry tool, project the 2 large circles and the outer circle of the disk. These will serve as reference points for the sketch. Then click on the View section icon to see the image clearly. Using the Line tool, draw 2 radii from the center of the disk. These lines should align with the centers of the small circles. To do that, select the center of the circle and the radius, then apply a coincidence constraint. Do the same for the second radius. Now, still with the line tool, draw a line from the center of the disc to the approximate middle of the opening. Use the dimension tool to measure the angle between the two radii. You should get 22.5 degree. Right-click to cancel it. Then, use the dimension tool again to set an angle of 11.25 degree between the center line and the lower radius. Also set a horizontal length of 87 mm for the center line. Now select those three lines and convert them into construction geometry. Next, we'll draw the shape of the cutout using 3-point arcs. Starting from the top point, draw 2 arcs that follow the contour down to the midpoint. Repeat the same for the bottom half. Then select the 2 top arcs and apply a tangency constraint between them. Also apply a tangency constraint between the top arc and the large outer circle. Now select the top midpoint, the center line, and the bottom midpoint. Then apply a symmetry constraint. Repeat this for the top and bottom endpoints as well. You'll likely see an error message appear. That's fine. On the right-hand side, click the number shown in parentheses, then click Delete. Use the dimension tool to set a diameter of 22 for the top arc and 34 for the second arc. Then select the 2 arcs on either side of the center line and apply an equality constraint. Do the same for the 2 outer arcs. The sketch should now turn fully green, meaning it's fully constrained. Finally, use the arc tool to create a new arc on the right side of the disc. Select the top point of that arc and the top radius, and apply a coincidence constraint. Then select the top point of the arc and the first green arc and apply a coincidence. Repeat this with the bottom point. Lastly, select the large arc and the outer projected circle and apply an equality constraint. The sketch should now be fully green and closed. You can then click Close to confirm it. With Sketch 5 selected, click on the Pocket tool. In the panel on the right, change the type to Through All and check the box Symmetric to Plane. Then click OK to confirm the operation. We're now going to repeat this cutout around the disc. To do that, select Pocket 4, then click on the Polar Array tool. In the panel on the right, under the Axis section, choose Select Reference, then click on the yellow line in the viewport. Next, set the number of occurrences to 16, and click OK to confirm the operation. To finish the modeling, we're going to add a small fillet on the outer edge of the disc. Select a small edge on the outer part, then click on the Fillet tool. In the panel on the right, set the radius to 0.2. Click Select, then add a bottom edge as well. Click Preview to see the result. And finally click OK to confirm. We're also going to add a fillet to the sharp inner edges of the center. Hold Ctrl and select all the relevant edges, then click on the Fillet tool. In the panel on the right, set the radius to 3, then click OK to confirm. We've now finished the reverse engineering of this bicycle disc. And to prove how accurate the modeling is, I'll use the FC info macro to get the weight of the part. By selecting the final fillet and setting the material to metal iron, we get a weight of 162.45 grams, which is very close to what I measured on my kitchen scale. Now you can use this part either to include it in an assembly or even run a thermal dissipation analysis, like the one you see on the FreeCAD splash screen. I hope this video helped you on your FreeCAD journey and gave you the tools you need to do your own reverse engineering projects. Thanks a lot for your attention.